Everyone is investing in AI companies. Almost nobody is paying attention to the industry making AI possible. The next trillion-dollar industry will not be artificial intelligence itself. It will be the power grid that keeps every server, every chip, and every data center running around the clock. That is the story we are telling today, and once you hear the numbers, you will never look at a data center the same way again. For the last 3 years, the entire world has been obsessed with chips. Everyone talks about GPUs, everyone talks about training runs, everyone talks about the next model that will change everything. But behind every one of those headlines sits a quieter, heavier truth. Artificial intelligence does not run on ideas, it runs on electricity. And right now, the electricity side of this story is growing faster than almost anyone predicted, which means the real fortune may not be built by the companies writing the software. It may be built by the companies keeping the lights on behind it. Let us start with the pillar that started this whole conversation. Artificial intelligence is quietly becoming a power problem. A modern AI server is nothing like the boxes that used to sit quietly in a corporate server room. These new systems are packed with GPU clusters running at extreme density, generating enormous heat, and pulling far more electricity than the equipment they replaced. Goldman Sachs has pointed out that these AI server systems draw dramatically more power than older architectures, and Deloitte has said the same thing from a different angle, noting that AI data centers require both far more electricity and completely new cooling approaches compared to a typical facility. Even the International Energy Agency, one of the most conservative and cautious institutions in the world, has said openly that artificial intelligence is already changing the electricity outlook for data centers and for entire national grids. So how big is this, really? The International Energy Agency projects that global electricity demand from data centers will more than double by the year 2030, climbing to roughly 945 terawatt hours, with artificial intelligence identified as the main driver behind that growth. Let that number sit for a second. We are not talking about a small technology sector quietly using more power in the background. We are talking about a demand curve steep enough to reshape national energy planning. Goldman Sachs, working the numbers from a different direction, estimates that data center power demand in the United States alone could rise to 8% of total American electricity consumption by 2030. To support that, the bank estimates the country will need roughly 47 gigawatts of new generation capacity, and something in the neighborhood of $50 billion in fresh capital investment just to build it. Deloitte adds another data point to the pile, estimating that AI-specific data centers could reach around 90 terawatt hours of annual electricity use as early as 2026. Here is the part that should make you sit up straight. This growth is not slowing down because chips are getting more efficient. Yes, efficiency is improving. Every new generation of hardware does more work per watt than the one before it, but the number of servers being built and the total amount of compute capacity coming online is expanding faster than those efficiency gains can offset. Training massive models and running constant inference for hundreds of millions of users at once creates a demand curve that keeps climbing even as engineers make each individual chip smarter. It is the same pattern we have seen in other industries before. Better engines did not reduce total fuel consumption once cars became common in every driveway. They simply allowed more cars to exist. Artificial intelligence is following the same road, just with electrons instead of gasoline. Let us put some of these numbers into terms that actually mean something outside of a spreadsheet. 47 gigawatts of new generation capacity does not sound like much until you realize that a single large nuclear power plant typically produces somewhere around 1 gigawatt. That means the industry may need the electrical output of roughly 47 full-sized power plants, built or repurposed within the span of just a few years, purely to keep pace with data center demand in one country. $50 billion in capital investment is not pocket change either. It is close to the entire annual budget of a mid-sized national government, poured almost entirely into wires, turbines, and cooling towers rather than into chips or software. When you translate the terawatt-hour projections into everyday language, you start to see just how large this shift really is. 945 terawatt hours is roughly enough electricity to power a country the size of Japan for an entire year. And that is just the data center slice of global electricity demand, not the whole picture. This brings us straight into Pillar 2, and this is where the documentary really starts to separate from the headlines you have already seen 100 times. The biggest obstacle facing artificial intelligence right now is not computing power. It is not a shortage of chips. It is something far less glamorous and far more physical. Electricity, transformers, substations, transmission lines, cooling systems, switchgear, battery storage. These unglamorous industrial components have suddenly become some of the most strategically important assets on Earth, and almost nobody outside the utility industry saw it coming. Think about what it actually takes to bring a new data center online. It is not enough to build the building and fill it with racks. You need a connection to the grid strong enough to handle a load that can rival a mid-sized city. You need transformers capable of stepping that power down safely. You need substations to manage the flow. You need switchgear to protect the entire system from failure. And you need cooling infrastructure aggressive enough to pull heat away from thousands of GPUs running at full tilt, 24 hours a day, 7 days a week, with no holidays and no slowdown. Goldman Sachs has specifically pointed to lengthy interconnection queues and transmission permitting delays as major bottlenecks slowing this entire build-out. Their own example from Northern Virginia, one of the densest data center regions in the world, shows how quickly a single region's demand can force utilities and regional grid operators into emergency mode, scrambling to upgrade infrastructure that was never designed for this kind of load. Picture a single hyperscale campus, the kind of facility a company like Microsoft, Amazon, or Google might build to support its AI ambitions. A campus like that can require as much continuous electricity as a small city, sometimes measured in the hundreds of megawatts. That is not a demand a utility can simply absorb overnight by flipping a switch. It requires years of planning, permitting, and construction, and in many regions, the queue of companies waiting to connect new loads to the grid stretches on for years, not months. This is the unglamorous reality behind every announcement of a new AI data center. The press release talks about compute capacity and model training. It rarely mentions the 3 or 4 year wait for a transmission upgrade, or the negotiations with a regional grid operator over how much strain the local substation can actually handle before something breaks. In other words, the real bottleneck is not the chip, it is the path from the power plant to the server rack. You can have the most advanced processor on the planet sitting in a warehouse, and it means absolutely nothing if there is no transformer capable of feeding it, no substation capable of routing power to it, and no cooling system capable of keeping it from melting under its own workload. This is why an entire category of industrial companies that most people have never heard of is suddenly being mentioned in the same breath as the biggest names in technology. Which brings us to Pillar 3, and this is the part where we follow the money. If artificial intelligence cannot exist without a functioning power and infrastructure stack, then the companies supplying that stack become critical players in the entire AI story, whether the public notices them or not. Let us walk through who these companies actually are and what layer of the system each one occupies. Constellation Energy operates one of the largest nuclear fleets in the country, and nuclear power offers something hyperscale data centers desperately want: reliable baseload electricity that runs around the clock without depending on wind or sunlight. GE Vernova sits deep inside the power generation and grid equipment world, supplying turbines and grid products that utilities rely on to keep the system stable as demand climbs. Siemens Energy occupies a similar space in electrical infrastructure and grid equipment, much of it centered in Europe but increasingly relevant wherever new capacity is being built. ABB brings electrical equipment, grid automation, and power distribution technology into the picture, the kind of unglamorous engineering that keeps entire regional grids from collapsing under sudden new loads. Then there is the layer closer to the data center floor itself. Schneider Electric focuses on power management, distribution, and cooling controls specifically built for data center environments. Eaton supplies switchgear, electrical distribution equipment, and backup power infrastructure that keeps facilities running even when something upstream fails. Vertiv is almost entirely built around data center cooling and thermal management, along with the power systems that support it, which places the company directly at the intersection of everything artificial intelligence needs physically to survive. Quanta Services handles the unglamorous but absolutely essential work of building and upgrading transmission lines and grid infrastructure, the literal physical work of connecting new power sources to new demand centers. On the energy storage and battery side, Tesla Energy has been expanding its grid-scale battery products, helping balance variable renewable generation with the kind of storage that smooths out supply and demand. CATL and BYD both carry significant exposure to battery storage and power electronics, technologies that matter enormously as more of this new generation capacity comes from renewable sources that are not always available on demand. On the generation side, NextEra and Vistra both carry heavy exposure to utility-scale power generation, with NextEra leaning into renewables and Vistra carrying significant natural gas and broader power market exposure. And then there is nuclear, which deserves its own spotlight because of how directly it connects to the hyperscale data center world. Cameco, as a major uranium supplier, stands to benefit if nuclear demand rises and existing plants extend their operating lives to meet new baseload requirements. Further out on the horizon sit companies companies like Oklo and NuScale, both working on small modular reactor technology. These companies are still early stage, and the technology is still unproven at commercial scale, so this part of the story is genuinely speculative rather than verified fact. But the fact that hyperscale technology companies are even having these conversations with nuclear developers tells you how seriously the industry is taking the baseload power question. It is worth pausing here to make something clear, because a documentary like this only means something if it stays honest. Not every claim in this story carries the same weight of certainty. Some of what we just covered is verified fact, backed by measured data from organizations like the International Energy Agency. Some of it is industry consensus, the shared understanding among analysts that more compute simply requires more power and more cooling. Some of it is independent analysis, like Goldman Sachs projecting where the downstream gains in utilities and infrastructure might land. Some of it is company statement, hyperscalers publicly announcing new power contracts and new infrastructure investments. Some of it is projection, forecasts built on current trends that could shift as technology evolves. And some of it, particularly around small modular reactors and which single company eventually captures the most value, is honestly still speculation. A good documentary does not blur those categories together. It respects the difference between what we know and what we are still watching unfold. It is also worth naming the companies actually building the AI models themselves, because they sit on the other side of this equation as the customers driving all of this demand rather than the suppliers meeting it. NVIDIA remains the core chip supplier behind most of the AI boom, and even its own hardware roadmap shows rising power draw with every new generation, which is part of why this entire infrastructure conversation exists in the first place. Microsoft, Amazon, and Google are the three largest hyperscale cloud operators on Earth, and each of them has become a massive driver of new data center construction and new electricity demand in the regions where they build. OpenAI continues to push demand for compute and infrastructure through its own model development, while a company like xAI is frequently mentioned in discussions about the energy bottleneck facing new AI developers, though detailed public data on its specific power arrangements remains limited. These companies are not villains in this story. They are simply operating at a scale where their success depends entirely on a power supply chain that was never designed to grow this fast, this suddenly. Now let us move into Pillar 4, because this is where all of these pieces click into place. Every single AI breakthrough you have heard about, every impressive new model, every viral demonstration, ultimately depends on physical infrastructure that has nothing to do with software engineering. Electricity, grids, cooling, power electronics, transmission, battery systems, industrial equipment. None of that shows up in a keynote presentation, and none of it gets applause on stage, but without it, none of the software exists in any usable form. A brilliant model sitting on a hard drive with no power to run it is just a very expensive file. This is the uncomfortable truth that the entire AI industry is built on top of a physical foundation most people never think about, and that foundation is now under more strain than at any point in its history. Here is a question worth sitting with for a moment, and honestly, we would love to hear your take on this in the comments. If electricity becomes the true limiting factor on how fast artificial intelligence can grow, does that change who actually wins this decade? Is it still the company with the smartest model, or does it become the company that secured the most reliable power contract 5 years before anyone else even thought to ask? That is not a rhetorical question. Nobody fully knows the answer yet, and that uncertainty is exactly why this space is worth watching closely. There is a historical parallel worth mentioning here, because none of this is entirely new. Every major industrial revolution in history has followed a similar pattern, where the flashy new technology gets all the attention, while the unglamorous infrastructure underneath it quietly becomes just as valuable, sometimes more valuable. When railroads swept across entire continents, the companies laying steel track and building bridges often ended up just as important as the railroad operators themselves. When the internet exploded in popularity, the companies laying fiber optic cable and building data centers became foundational players, even though almost nobody watching a website load ever thought about the cable underneath the street. Artificial intelligence appears to be following that same pattern now, except this time the underlying resource is not steel or fiber. It is raw electricity and the physical equipment required to generate, move, and manage it reliably at a scale the world has never attempted before. Which brings us to the final pillar, and the real answer to the question this documentary opened with. Why could electricity infrastructure become one of the fastest growing industries of the entire AI era? Look at the numbers again, all together this time. Global data center electricity demand more than doubling by 2030, according to the International Energy Agency. AI-optimized data centers specifically projected to more than quadruple their electricity demand in that same window. United States data center power demand potentially reaching 8% of the entire country's electricity consumption, roughly 47 gigawatts of new generation capacity needed just to keep pace, backed by an estimated $50 billion in capital investment. Goldman Sachs projecting AI power demand could climb by roughly 200 terawatt hours between 2023 and 2030 in its base case scenario. And Deloitte pointing to AI data centers potentially consuming around 90 terawatt hours annually as soon as 2026. Stack these figures side by side and a pattern becomes impossible to ignore. Every credible institution studying this question, whether it is a government-backed energy agency, an investment bank, or a major consulting firm, keeps arriving at some version of the same conclusion: that electricity demand tied to artificial intelligence is climbing faster than most planners expected just a few years ago, and that the infrastructure required to meet it is not yet fully built. Every one of those numbers represents new transformers that need to be built, new substations that need to be energized, new transmission lines that need to be strung across entire states, new cooling systems that need to be engineered and installed, new battery storage that needs to be manufactured and deployed, new generation capacity, whether from natural gas, nuclear, or renewables, that needs to come online faster than most utilities have ever moved in their entire history. That is not a side story to the AI revolution. That is the AI revolution, just measured in gigawatts instead of parameters. Artificial intelligence may absolutely become one of the largest industries in human history. Nobody watching this is being told to bet against that. And this documentary is not an argument that software and models do not matter, because clearly they do, and clearly they will keep reshaping entire industries for decades to come. But every single AI breakthrough, every model, every application, every product built on top of this technology depends on an even larger physical system quietly working underneath it. The companies building electricity generation, transmission, cooling, batteries, and industrial power equipment may ultimately end up among the biggest winners of the entire AI era, even though almost none of them will ever appear in a keynote presentation about the future of intelligence. The future of artificial intelligence will not be decided only by who writes the smartest code. It will also be decided by whoever supplies the energy and infrastructure that keeps that code running, day and night without interruption for years to come. And that is a story worth understanding, because the ripple effects of this shift are going to reach further than most people expect, including into the vehicles sitting in your own driveway, as power demand, grid capacity, and industrial supply chains all start competing for the same resources. So that you are not caught off guard by what comes next in this industry, join us here, because this is only the beginning of the story.